let's go and do another problem, another thing now. We will, this thing, do you notice that this distance keeps coming up all the time? Right? And quite often, or basically our intuition often deals with Euclidean distance. Now, there's a bit of bad news I'll mention. When you come to distance, especially with Euclidean distance, but generally with all distances, there is a problem. It is called the curse of dimensionality. I will start with the curse, and then I'll talk about another class of algorithms called nearest neighbor methods. So what is this curse of dimensionality? It sounds like a Harry Potter curse, right? Terrible curse from a Harry Potter story or something like that. So, well, it is this. I'll mention a fact. Tell me if it sort of agrees with your intuition. So think of 10 friends in your mind. Actually do that experiment in your mind. Write down the names of your 10 friends and remember where they live. Right? So just write it down on a piece of paper, 10 friends, actually do it, and write down where do they live. I'll let you do it for 5 minutes.
What if we don't have 10 friends?
10 acquaintances. If enemies are allowed to.
Now I have a lot.
And take them from around the country. Like, don't just say 10 of my neighborhood friends. Take friends who live in other cities. Make sure that you don't pick friends from the same city. Just make sure that all friends are from different cities. And any country is okay if you want. But no two friends should belong to the same city. Are we done? Are you still writing? Some of you are still writing.
My two friends lived in the same household.
No, that's not allowed. All right, guys. Those of you who are on Zoom, are you also doing this exercise? Please do it. It's a fun thing. Did you do that, guys? Are we done? Yeah. Okay. Now, make an interesting observation. How many of them live either next to the state border or next to the end of the land, next to just the ocean or one of the big lakes? In US, the lakes themselves are practically the sea, size of seas. How many of them live next to that, very close to that? They don't live in the center of their states, but they live on the edge towards the boundary of the state. Put tick mark against people who are reasonably close, let's say within 30, 40 miles of the boundary of the state. Or next to the sea or something like that. Sea next to a big lake, Lake Michigan, Lake Erie, something like that. Let me know when you're done. It's just tick marking them.
Six out of 10, yeah.
6 out of 10. Anybody else?
Same. But different friends.
Yeah. In your case? 3 out of 10. Oh boy.
9 out of 10.
9 out of 10.
3 out of 10.
3 out of 10. Okay. 6 out of 10. Okay. So the reason I asked you this, the general observation is, in my case, whenever I look at it, everybody seems to be near the sea or the end of the state or something like that. And here's an explanation for that. So obviously, 10 is a very non-representative number. If you do it with 100, this becomes more obvious. But look at this experiment I'm going to do. Imagine a circle. I hope I know how to draw my circle. Shame on me. I used to be an artist and could draw pretty good circles. Okay. So suppose your friends are uniformly distributed in this circle, right? Imagine that land is a circle and your friends are uniformly distributed. So this topic, by the way, I'll spend some time on this topic because it is interesting. So imagine this is a uniform distribution. I hope I've made it reasonably uniform. If your friends are uniformly distributed, I'll just say points are uniformly distributed. I ask this question, where do half your friends live? So you would say, well, this is an area. I will look at this, right? I will ask what radius, how far do I have to go from the center of the circle to include half my friends, right? So you would say that, see, this is a pi little r squared, and let's say that the outermost radius is capital R, right? Let me, for sake of argument, without loss of generality, I can say capital R is 1. I scaled it down to a unit disk. Is that okay? Are you convinced that I'm not cheating? I can just scale it down, shrink the picture down to a unit disk. Well, states don't look like 1 inch long, but imagine you can project it down onto a map and it will look 1 unit long, 1 unit circle, right? Now comes the interesting. What is the area? You would agree that to get 50% of friends, you would need to have the inner area A should be a half. Would you agree? To reach half your friends, you need to cover half the area. We all agree with that, right? So now the question is, when do we reach half? You know that the area of the circle is pi r squared, right? And to reach over, and pi is the total area of this. What is the total area of the whole disk? Pi, right? So this should be a half, isn't it? Right? And so what does it mean? R squared should be a half, and R is equal to the square root of a half, and that is equal to 0.7, isn't it? Which should be a surprise. You would have thought I would have to go half as far, half the distance, isn't it? But you notice that you had to go 70% of the distance to get half your friends, which means that other half of your friends live in the 30% of the distance to the boundary, right? They live here. Half your friends live in that outer circle, more than half. I mean, say half of your friend lives out there and only half your friend live in the center, right? This gets, so this is 0.7 and this is 0.3. There's an asymmetry, right? This is much bigger distance and this is much smaller distance. Now imagine that we are little particles in a sphere. Well, states don't look like spheres, but now that metaphor is beginning to break. But imagine how far do you have to go from the center of the sphere to reach half the friends if they were all scattered inside the sphere, right? So there what would happen is the volume of a sphere is 4/3 pi r cube, right? And let's say that this radius is 1 again, and the volume of the entire sphere is 4/3 pi, isn't it? So these constants go away. You would say that this needs to be half, and so r is equal to cube root of 1/3. Can somebody tell me what that is? 0.79. So let me start writing it. When it is a dimension 2, dimension 1, suppose all of us lived on a line uniformly spread. How far would you have to go to get half your friends? 50%, right? So you would have to go 0.5. Now, for 2 dimensions, you would have to go 0.7. 0.3 dimensions, you have to go practically 0.8, right? Up to the first decimal place. Now, imagine, likewise, generalize it to, let's say, a 10-dimensional sphere, right? A hypersphere. And if your friends are scattered inside a 10-dimensional hypersphere, how far do you have to fly to reach and meet? In what region would you find half your friends? So then r to the power 10 would be half, and r would be a half to the power 1/10, isn't it? And could somebody tell me what is the 10th root of half? 0.93. So you notice that, which means that half your friends seem to be sitting on the edge of the sphere, isn't it? Do you see this, guys? That in the tiny 0.7% of the distance from the center, way out there at the edge, most higher and higher dimensions, something funny happens. Most of your friends seem to be living, I mean, not most, half of your friends seem to be living here. Do you see that, guys? Right? And what happens when you reach, we are dealing with data sets. What is the data set that we dealt with most recently? Housing. We had how many factors were there? Breast cancer. Breast cancer, right? It had about 30 dimensions. So let's find out what is half to the power. So now you realize that the radius you have to go to is half to the power 1/d. D is equal to 30. What is the value you get? 97.7, so practically 98. So what do you notice? And we have just gone to 30 dimensions. But these days, we deal with data typically in no less than 100 or 1,000 dimensions. And natural language processing is very common for us to, and computer vision, very common for us to deal with at least 1,000 dimensions. So let's go 1,000. Can somebody tell me what is the 1,000th root of half? What does it tell you, guys? That to reach even half your neighbors, you have to practically go to the edge of the sphere, hypersphere, isn't it? Because it seems that other half are practically camping out there on the very edge, it seems. And why is that so? The reason it is that as you increase, imagine this, you have people on this point. One intuition I can give you is, imagine your friends are sitting here. Then you have to go half the distance. See, look at this. You have to go half the distance. Well, let me cheat a little bit here. Yeah, this is your origin. Now, suppose you bring in one more dimension. Or, well, it was a circle, so I shouldn't bring in a rectangle to confuse. Oh, sorry. Yeah, so suppose I make this into a big round circle. Now, all the same 4, 1, 2, 3, 4 neighbors, well, this is not a good circle. I apologize. This is a terrible circle. I have to make a much bigger circle. This circle. You want to uniformly distribute your 8 friends. Where will they go? They will all be all over the place, right? Take a little bit of an argument to convince yourself. So here, let me just do it better this time. 1, 2, 3, 4. 1, 2, 50%. Now, if they scatter all over the place, does it look like intuition that you really have to go far to meet your friends? There is just way too much space. They will just fly off all over the place. And you have to go rather far to go meet half your friends, right? Much further to meet half your friends. So in other words, in higher dimensional spaces, there is just way too much space out there, right? When there is too much space, it creates problems. Problem that it creates is higher dimensional spaces are sparse. Do you notice that one line is dense, but in 2 dimensions, the points have just scattered, flown away. Higher dimensions, they'll even more flown away. And so assuming uniform data or uniformity of data, you would realize that your friends are all really very far away and that space becomes very sparse. Right? Now, in reality, as we know, when we are clustering, data is not uniform, it's non-uniform. Otherwise, there won't be any clustering that we can do. We all agree with that, hopefully, isn't it? If data was truly uniform, there are no clusters. You have to go with the assumption that data is non-uniform. So it turns out that so this problem is called the curse of dimensionality, that in higher dimensional spaces, you need a tremendous amount of data. Whatever data you have, it looks sparse, right? So when that happens, your question of neighbors begins to break down, right? You don't have real neighbors. It's like, in Bay Area, if you want to find your neighbor, you have to go, well, the way the houses are these days near each other, you probably have to stretch your hand from the window and shake hands with your neighbor, right? It's that close. But in the case of, suppose you were living in, I don't know, Idaho or somewhere like that, in a large farming area, to go to a neighbor means getting into your car and driving for half an hour, right? Those are very sparse regions. So then it sort of begins to dilute the meaning of neighbor itself, right? That's a problem. That is the curse of dimensionality. Now, how does it affect clustering in particular? It turns out that some algorithms are more robust and some less. A k-means has a few problems. I mentioned k-means. So I would like to go back and revisit some aspects of k-means. Yes.
So how is this connected with the law of large numbers?
Law of large numbers doesn't come in. It's unrelated. No relationship. No obvious relationship. You can, of course, start connecting the dot, but you wouldn't see a law of large numbers. Just say that patterns will be stable, visible. Patterns will emerge and you can trust the patterns. Okay. So, well, that's one way of putting it. Actually, let's not get there. At this moment, k-means, let's say k-means we are there. Right? One of the problems with k-means was, remember, instability. If you take different initialization points, you can end up with different problems, disadvantages. The second problem was that it has no outlier ability, outliers. No outliers. Another problem with k-means, is that, so suppose your data has outliers, these outliers, suppose you have this, and you try to find a centroid. Where will the centroid be? Will it be truly in the center? Or will it get pulled towards the outlier? So suppose it declares this to be the cluster. What will it do to the centroid? It will get pulled towards the outlier, isn't it? Right. Okay, let me make this thing very obvious. Whenever you look at averages or centroids, or centroid is in one dimension, it is basically your average, right, of locations average. Think of make it very real. If you ask yourself in your company, what is the average salary that people make in tech companies? When you look at the average salary, you might be surprised that you're making less than the average. Why is that so?
The CEO takes a whole bunch of money, 40 times more.
Yeah.
Exactly. A CEO will take home $800 million, and his pack of wolves, like which you call the executive staff or the C staff, will take another maybe 100 million each or 50 million each, right? So I'm sorry for being, take it in a lighter way. Okay. And then when you look at your paycheck, all of a sudden it doesn't look as good anymore, right? So averages are skewed by big numbers. The average salary in these companies is not representative of what employees really make. So how do you stabilize against that? You take the median salary. If you really want to know what is the salary, you can take the median, you can take the harmonic mean, you can take geometric means, you can do some things, but median is often commonly used. That is why if you notice in US and every place in economies, when people are asking for incomes or anything, income especially, the census data always looks at the median household income, never the average household income, right? Looks at the median. And so a k-means is susceptible to outliers for exactly the same reason. You're averaging. Your centroid is just a high dimensional average location mean, right? Now, the way to then say, well, all right, I'm not going to do k-means. I will define my center of the cluster to be the median, right? So then you start key midwives and so forth. There are other alternative adaptations you start doing, and they are adaptations. But one of the problems, deeper problems, is in higher dimensions, because quite often you use the Euclidean distance, what happens is that there's a peculiar problem that you face. All points seem to be equally far apart. It's very hard, actually. So the way to look at it is, if you look at the pairwise distance between all points within a cluster, or just not even just the whole data set, you look at the pairwise distance and actually square it. There's a word for that. It's called dispersion. Right? A fancy word, just square of distance, right? So in a way, when you did WSS, right, in a way you're looking at the dispersion. So all right, xi, xj. When you look at the dispersion of ij, when you look at the dispersion measure, and you plot the dispersion, you build a histogram in lower dimensional spaces, you may find that things have a bell curve, reasonably wide bell curve structure, right? Then, and the average, so suppose this is 0, 0, 0. There is somewhere the mu is there and somewhere the sigma square is there. Am I making sense, guys? Bell curve, looks common sense. In high dimension, what happens is, or data may not even be actually like this. What happens is data, no, I take that back. It is more like, this is more likely to be true. This is more likely to be true, right? Because obviously they're clusters. So these are distances. So yeah, so something like this. What happens in high dimensions is that from this, and it is like mu is close to the origin. In high dimensions, this thing becomes, first of all, the distances, the average distance between points is huge, right? The mu, all points are far apart. They're sparse. And the other thing is the distance between all the points, they begin to look the same. In other words, they are all peaked, right? So, would you really consider that 2 points, 1 point is at 1 light years away from you, and another point is 1.001 light years away from you? Would you consider that one belongs to the cluster and other doesn't? You wouldn't, right? You wouldn't. So a very similar intuition applies. What happens is in high dimensional geometry, our points become almost the same distance from each other. So detecting clusters becomes much harder, right? That is one of the problems that you have with k-dimensional data. So what should you do? Give me a moment, guys. I'll raise stand up. Okay, so what happens is when you try to apply clustering algorithms directly into high dimensional data, two problems comes. One is that it is terrible computationally, very, very expensive, right? Well, that is not bad enough. What is worse is all that expense would be worth paying, especially, by the way, when you're doing these computations in the cloud, it means real dollars and cents, right? You rake up a bill. So let's say that you would do that. You would say, well, all right, what is the benefit? It turns out that these algorithms, they begin to do a little poorly. K-means in particular begins to do very poorly with Euclidean distance. So a lot of people have studied it, and there's a whole body of work, on this problem of high dimensional spaces. Today, all we can say is we are beginning to understand high dimensional geometry, right? We don't really have as strong an intuition of high dimensional geometry as we would wish. We are beginning to understand it. You'll see a lot of interesting books coming out on high dimensional probability theory or high dimensional statistics and so on and so forth. People are beginning to get a sense. So sometimes people point out that, see, data truly is not uniformly distributed. So this argument may not be true. There may be there are clusters there and so forth. But the curse of dimensionality is real. You have to struggle with it. And k-means does weaken, becomes problematic. Euclidean distance does very poorly in high dimension, right? If you look at the dispersions, the variance is all just too tight. Variance is too little. All the distances begin to look the same, more or less, right? And they're all big distances. So not a nice situation to be in. So what should you do? Well, that brings us to an interesting topic, dimensionality reduction. What you can do is you can project the data down to a lower dimensional space. Right? How do we do that is an interesting topic. There are many methods, the simplest of them being principal component analysis. At some point, we will do it in this workshop, but not for today. So the idea, the right approach is that use something else. First, reduce the data, project the data down to a much lower dimensional space. Once you have projected it down to manageable, like for example, first try whatever the data, try it out in 2 dimensions and see how does it look. Doesn't look good? 3 dimensions, how does it look? Well, when we do PCA, we'll go through a more formal process of finding what is the right number of dimensions, and our elbow method and scree plots will come back. But there is a way to determine what is reasonably good. There are many methods to do dimensionality reduction. It's a big topic in its own right. We'll cover it separately. But given the fact that those techniques exist, whenever you see high dimensional data, your first temptation shouldn't be just to go cluster. Your thing should be, let me first reduce the dimensionality, because clustering would be probably more effective in lower dimensional spaces. Are we together, guys? The other thing is that sometimes use alternative algorithms. So for example, graph algorithms tend to do much better in higher dimensional spaces like that. For example, there is a method today we are running. I have 15 minutes. One of the methods I wanted to teach is spectral. Maybe I'll do that after lunch. but after lunch we have a lab. Okay, if time permitting, I would like to do this method, clustering. It is inspired by graphs, right? It basically uses something called eigenvalue decomposition. And eigenvalue decomposition must be very familiar to those of you who attended my math class or from your college textbooks, if you remember that. Eigenvalue decomposition of something called the Laplacian matrix or Laplace matrix. Laplace matrix, Laplace matrix. It comes from graph theory. And you can use that to cluster data. Now, it's a little bit of a big topic, just like density-based clustering. It will take its own couple of hours to, or maybe at least an hour. Time permitting, we'll do it today, but not now. So one of the things you could do is try out spectral clustering or density-based DENQ, etc. also work reasonably quite well, actually. You can try that out. So there are many clustering. I'll end today by saying there are many clustering methods. Right. What you should do is, and this is where the fun is, which method works takes a lot of trial and error, There are no perfect things. Typically in a domain, once you have hit upon a good one, you sort of stick to that. It isn't that next month's data will require a different algorithm. It doesn't work like that. One domain's data, quite often after a lot of trial and error, you'll find that this tends to work on this problem. Right, so try out many methods. There is Birch. I didn't teach you Birch. There's Birch. There are many methods, that clustering methods that we can use. So, but I will summarize by saying we studied k-means clustering. Its softer sort of a version is called expectation maximization, which also we didn't do. I'll try to do it in one of the Tuesday sessions if time permits. Then we did agglomerative hierarchical clustering, and we did density-based clustering, isn't it? 3 classes of algorithms. And we talked about the curse of dimensionality, and we talked a little bit, just glancingly, that there are other algorithms, like for example, the spectral clustering algorithms that use eigenvalue decomposition of the Laplace matrix. Now, what in the world are these big words? If you're not familiar with it, just altogether ignore it for the time being. Okay? When the time comes, we'll learn about it properly. So that's all for the theory sections. We have 10 minutes. I would like to take questions.
If you alluded to using a graph-based approach,
Spectral, yeah.
for spectral clustering, trying to double-click a little in terms of understanding the how it translates in terms of the underlying data structure. Is it because when we assume a graph-based approach for each of the nodes, they're likely to have multiple attributes, and there's a notion of what each of those attributes are and the significance in the domain?
Not necessarily.
Choose which ones to make participate inside a distance function.
Hold those thoughts in your mind. I want to do it properly, right? Because I need to build to it. Slowly build to it. Spectral clustering deserves a session of its own.
So
Let me do it.
At least build an institution. Is it a mathematical technique to get around the problem, or is it a technique where you're able to use more attributes and get close?
No. It's a mathematical technique. It's a mathematical technique. It's pretty elegant. See, what happens is clustering or a topic like this. Do you notice that classification? People can bring completely radically different approaches or ideas to bear upon a problem. Right? The way hierarchical clustering thought of the problem is entirely different from the way k-means thought. And the way density-based methods thought about it is entirely different, isn't it? So the beautiful thing with machine learning is people bring very different approaches and ways of looking at it. And they build it up and they have success. When they have success, then you have to sit and parse, okay, what are the strengths and weaknesses of it? And sometimes they have surprising strength that other algorithms don't have. Right? So when you take graph-based, and these days, by the way, graph-based machine learning is all the rage. It's the hottest thing. right? So graph-based, we are realizing actually that graph-based approaches to machine learning have been somewhat underappreciated, and they really need far more attention that we have been giving. And they're getting those attention now.
So I have one basic question on a dimension here.
Yes.
So our physical dimensions are just 3, right?
Right.
And what we can read, even with instruments, is basically 3 dimensions.
No,
And
no, no,
yeah,
no.
yeah,
Like
yeah,
that.
yeah. Just complete this one question here. So this is only in space dimensions. Of course, there are other dimensions you are looking at in terms of other things which we could not perceive, right? So
Right.
is dimensionality reduction, reducing all those and trying to get down to what we perceive? Is it, can you visualize like that?
No, no, not like that. Let me make it real to you. See, when you think of space, yes, it is true, X, Y, Z, right? 3-dimensional. You can go sideways, you can go forward, backwards, you could go up and down. And that about limits it up. But that is space, nature of space. And if you bring in time, space, time, it is something that we as human beings are embedded in. But when you think of data, it lives in a different space. So for example, let me give you an example, a very real example. In one of the early projects that I worked for NASA, we looked at all sorts of things. So one of them was, okay, let me make it very real. Why go there? Very real. So suppose you're looking at it, temperature, pressure, right? Wind speed, wind, right? Wind speed, humidity. Now you need one more dimension, humidity. So now any observation, so suppose you take an observation, you realize that it will have temperature, pressure, humidity. We did the weather data, and speed, wind speed.
Okay.
So what are you looking at? Each data point exists. So you have a value here, some values here. So each row exists in what space? Each of these is a scalar field. This is R, this is again R, R, R. Technically, any point is a tuple. In the abstract sense, this.
Right.
It is some temperature value, it is some pressure value, some humidity value, some wind speed value. So this exists as a point belongs to a point in a 4-dimensional space. But it is not real space. It is the space of these measurables, measures, isn't it? Data measurable. So that's how you think of higher dimension. Data comes in high dimension. You're not thinking of space as it is. So that's why people use the word high dimensional spaces. But when we use the word spaces in machine learning, we almost never mean the genuine space that we occupy as human beings. We mean the data space like this, measurable space of measurables. So
dimension is basically a parameter that you're providing into the problem, basically.
That is right. Yeah, it is the number of features you have. Literally, that's your dimension. Here I have 4 features: temperature, pressure, humidity, wind speed. So my data is 4-dimensional.
Okay, 4 dimensions, but when we thought of dimensions, we looked at circles and spheres. That's basically a spatial representation of these. How does it translate to that?
Very simple, because the geometry that we have in real space translates to this also. Yeah. In the abstract, you can see, for example, let's take just temperature and pressure. I can create a circle and say a temperature and pressure, the sum of them must be a T square plus P square must be less than some value, X, right? And so what have I done? I have said temperature and pressure cannot exceed a certain amount. Give me all data points which fulfill this constraint.
Okay, okay.
That is it.
Okay.
This is T.
So it's a solution domain that's more geometrical. Or problem domain is different.
Yes, yeah. So that's all it is. So what happens is that, see, when you come to machine learning, sometimes the way, in fact, is my fault also, and I try to avoid that fault. But the textbooks and all of these things, people come with a background see, there are two kinds of people who come into this. People who are coders. So they are very that, okay, forget all the theory, tell me how I code, right? So they're like, and to hell with how DB scan works. I just need one line of code. DB scan, this is the constructor, these are the arguments. What exactly do I need to specify? Epsilon and endpoint, and done. Right? This is the coder's perspective of machine learning. The trouble is these coders are not innovators, and they don't see the limitations of when it works, when it doesn't work. Basically, you have to go deeper in that. Then on the other spectrum are the people who come from deeply sort of a mathematical background, right? And they want to understand what is happening. And they always think of facts. See, there are two schools of thought in so, okay, I'll give you my background. Most of you know that I did my engineering. So maybe you can stop the recording, please.